Okay, well we've considered a few subgroups. I'm going to consider a slightly different subgroup, slightly different flavour of subgroup at least. I'm going to consider the set C of complex numbers but without the 0, which is equal to C star. And I'm going to consider the group of C star under just normal complex multiplication. So this is a group, I think we've seen it before, but I'm going to consider the subgroup H, which is complex numbers Z, non-zero complex numbers Z, such that mod Z equals 1. I'm going to show you how that forms a subgroup of the complex numbers under multiplication. Yeah, so what does it look like on the complex plane? If I just draw the real and imaginary axis, like that, real, I'm going to use a slightly different colour here, I'm going to use blue, then I'm considering numbers that are on the unit circle there with radius equal to 1. So what do they look like? Well, let me recall my definition. I'll go back to black here. I'll go back to black. Let me recall the definition of a subgroup. Oops. What we're going to say is that if X is a member of your subgroup H, then X minus 1 is a member of the subgroup H. And if X and Y are in the subgroup H, then X, Y is a member of the subgroup H. Here, there's no confusion. I'm just writing the group operation by writing the symbols next to each other. So juxtaposition, I guess the technical word is. So what does the number, if we talk about Z1, if that's a member of the set H, I'm going back to Z notation here, then the general notation for a complex number Z equals R e to the I theta, where this is the modulus and this is the argument here. But of course, we know that the modulus of the Z equals just the radius R, and because we're considering just Z with complex numbers with a modulus of 1, we know that R equals 1. And so if Z is in H, then that tells me that, or Z1 here is in H, that must be of the form e to the I theta, because I've got an R equals 1 there. So what have I got to show? I've got to show these two conditions are met here. So what is Z1 to the minus 1? Well, that's just equal to e to the minus I theta. I'll just verify that Z1 times Z1 to the minus 1. See how I casually use a dot there to indicate complex multiplication. I'm being a bit slack with my notation. I should be a bit more consistent, but it doesn't matter. It just reminds us that we're using regular complex numbers. Complex number multiplication equals e to the I theta, that's Z, or Z1 I guess. And this is Z1 to the minus 1, e to the minus I theta. So that's equal to, because the product, we've got the product of two exponentials, we've got I theta minus I theta equals e to the 0 equals 1, which is your identity, your multiplicative identity. So that one checks out. It doesn't exactly check out. I've just verified that that number here is in fact the inverse of Z1. But what I really meant to do, I got a bit carried away with that, what I really meant to do is to verify that Z1 to the minus 1, which was e to the minus I theta, is actually a member of the subgroup H. And we can tell because the modulus of Z1 to the minus 1 equals 1, because it's just 1 times e to the power something pure complex. So that checks out. And what about Z1, Z2? We've got to check that the product of two members of H equals is also a member of the subgroup. Well, we can say that Z1 equals e to the I theta 1 and Z2 equals e to the I theta 2. So Z1, Z2 equals e to the I theta 1 times regular complex multiplication I theta 2, which equals to e to the I theta 1 minus theta 2. Therefore, mod Z1, Z2 equals mod e to the I theta 1 plus theta 2. Should be a plus there, which equals 1. So we know that the product is in the product is a member of the subgroup as well. Okay, so there is our complex plane. This circle here forms our H, which is Z, such that mod Z equals 1. And it's a subgroup because it's closed under taking the identity element, taking the inverse, and it's closed under complex multiplication as well. Okay, I'm going to stop there.